Greetings. So, we summarized in the previous class the basis for what is called as classical computers. So, the term can sometimes be a little misleading, because this is what classical computing is called, but it does not mean that it does not use quantum devices. All the transistors and everything actually work on quantum theory. So, there is a element of quantum in the classical computers, and a very strong element, because all the devices make use of quantum devices. But it is classical because it is based on the 0 and 1 symbolic logic of George Boole. Okay? So, that is classical computing. And then we get into the era of quantum computing, and it started with Deutsch and Feynman. These were amongst the first ones who thought about this, and it came in the wake of the Church-Turing theses, because the work of Turing was so impactful that you could set up any computing problem, anything that logic can lead you to, okay, can lead you through, using an analysis, using machines, if you could solve it on what is called as a Turing machine. So, it became the signature of anything that can be done with symbolic logic at all. So, what the Turing machine does, it manipulates symbols on a strip of tape according to a table of rules. It is not necessarily a machine, but it is an idea, it is a logical set of ideas which can be implemented. And Turing made some great inventions which led to the field of artificial intelligence as we know it now, which is making a huge difference to technology. A programmable digital computer, one of the first computers was built on the ideas of Turing. Then he came up with what is called as the bomb, which was an early computer which cracked Germany's Enigma codes during the Second World War. And many of you may or may not know that breaking the Enigma code is thought to have shortened the war with Germany by years and saved millions of lives. So, it is not just electronics and arithmetic that got affected due to Turing's work, but it had major impact on the world history. So, millions of lives perhaps would have been saved by this. And then of course, he set up many things which started this whole technology of electronics and computers, all right. So, this work came, it was prompted by a question which David Hilbert had asked, and David Hilbert is known to all of you. So, Hilbert's question was, is there a general algorithm which mathematicians can follow to determine if a mathematical statement is provable? Okay, it is a very large question. It seems to be stated in very simple and very few words, but it is a very large question. And Turing's response was the Turing machine. Okay, the Turing machine really addressed this question, and what it does, that it provides you with the technology to answer Hilbert's question and says that yes, this is the algorithm, this is what you can do, and then you can do anything, any problem can be solved based on this, which is why the Turing machine is such a big thing. So, it was in response to David Hilbert's concern, and then of course, it has led to technology and very important frontier fields such as artificial intelligence, machine learning, which is a subset of that, and deep learning, which is a further subset of that. And these are the things that many of you would be using in your lifetime. So now comes a question, is there a universal computing device which can efficiently simulate any physical system? Now the emphasis, the key word over here is a physical system. And a physical system is one which follows, which can only be described by laws of nature, which is what governs the physical laws, how it evolves, all right. It describes its dynamics. And physical systems are not described by classical laws. Physical systems are governed by quantum laws. Okay? The classical laws are based on classical ideas, and now I am not talking about the 0 and 1 of George Boole. I am talking about the classical laws of nature, like classical physics, okay, like Newtonian physics, Lagrange's physics, Hamilton's physics, but not Schrödinger, Heisenberg or Feynman physics. Okay? So the physical system, any physical system is governed by physical laws, the laws of nature, and these are quantum laws. And this is the question which David Deutsch was addressing, that since quantum theory is what would govern the laws of physics, then you need to be able to devise a machine which is based on these laws. And he actually did come up with an algorithm, a quantum algorithm, which is the Deutsch algorithm. I will talk about it a little later. And in many ways, Deutsch can be regarded as the father of quantum computing, although Feynman also is credited with this recognition. He gave a famous talk in 1982, and he pointed out that quantum computers would provide an exponential speed up in simulation, because simulation of what? Simulation of a physical system, and the physical system is obeying quantum laws rather than classical. So Feynman came up with this brilliant idea, and then of course there were developments just about 10-15 years later. Peter Shor showed how to factor integers into primes in polynomial time using quantum method, and it would break the RSA encryption. So this was in 94, and then Lok Kumar Grover, he developed the quantum search algorithm, and this really triggered the era of quantum computing, and the first qubit machines were developed very soon after this, so around in the middle of 90s. So it's already a little more than 20 years now, and things are developing very rapidly in this area. So when you talk about computing, okay, when you're dealing with 1 or 0, it is like left or right, yes or no, okay, true or false, hell or heaven, north or south, okay. And if you think of a coin, it is heads or tail, or obverse or reverse, as it is called, all right. And if you toss a coin, if you begin with heads, what is the probability that you will get heads? That probability is half. What is the probability that you would get tails? It would also be half, right? And if you started with the opposite side of the coin, it would still be the same, okay. No matter what you are starting, you can hold the coin with heads up or tails up, and it is just one or the other, either heads or tail, either 1 or 0, either yes or false. The switch is either on or off. The cat is either dead or alive. Okay? There is nothing in between. And all the results of Boolean algebra, Carnot maps, Shannon's information theory, and the computing networks, they are based on this idea. Okay, everything is in terms of yes or no. All the logic that we talked about can be analyzed in terms of this 1 or 0. But then there are many shades between the black and white. Okay? And quantum laws are such that they need you to take into consideration a superposition of a state which is a superposition of the dead cat and also the live cat. This is what we have been talking about in our earlier discussions on quantum mechanics. Okay? We had this in manifestation of the Young's double slit experiment. We discussed the principle of superposition. We did it when we discussed the Feynman path integral approach, right? All of these things we have discussed earlier. And then we do quantum mechanics to simulate nature, means computation is done at the end to simulate nature. And Feynman said that these simulations would be faster and more effective if you used quantum computers, because the physical laws are of quantum nature. And they admit these alternative states together. So, if you pass light through a slit and through a polarizer and another polarizer which is orthogonal to that, orthogonal to the previous one, then you will get no light. But if you put a third polarizer in between, okay, which if the first two polarizers were stopping light, the third ought to stop it even more. But instead you actually get light at the end. This is because light is quantum. Okay? Now this is a very strange thing. If you have two slits and you have light going from one end through the other, you know that you get interference, okay, which is the Young's double slit experiment. But if you pass this light through polarizers, so what you are doing is you have marked, you know from which slit the light has come, and if you mark it, then the interference is lost. But if you put another polarizer which is at an angle at this, then the information about how light was polarized, that information is lost. So this becomes the eraser and the fringes reappear. We have discussed some of these things in the context of the Feynman path integral approach. At that time we discussed this which way marker experiments, the delayed marker experiments, right. So I will like you to revisit those ideas to remind yourself that quantum ideas are absolutely mind-boggling. They are very counterintuitive to begin with, but once you get used to it, then of course you know that okay, the nature is best described by these laws, and if it is so, then that is how you need to build your intuition. You have to factor in this principle of superposition into your intuition so that it is no longer counterintuitive. Okay. So I would like to refer to a part which is from an abstract of this famous paper by Peter Shor, who developed one of the first quantum algorithm, and this is straight from his paper. And what he says is that a quantum computer behaves in much the same way. The computation proceeds down all possible paths at once, and each path has associated with it a complex amplitude. And if you had just read this statement without looking at the source or the journal or the author and Peter Shor's name, you would have thought that, okay, this is coming straight out of a discussion on Feynman path integral approach to quantum mechanics. Okay? If something can happen in one way and another way and a third way, and there are multiple ways, including particle can go from here to there, and in between it goes to Mars and comes back, then it can happen that way. And this is the idea which Peter Shor has used, okay, which is what enabled him to develop the first quantum algorithm. And then very soon after that, Lok Kumar Grover, who studied at IIT Delhi and subsequently worked at Bell Labs, so he developed a search algorithm, and he could achieve much faster time of doing the search, order of square root rather than n over 2. Okay, so those are the huge advantages that quantum computing has led us to. So where are these advantages coming from? They are coming from the fact that whereas the classical logic gates are built from these binary digits 0 and 1, quantum gates are built from a superposition of 0 and 1. This is a quantum superposition of 0 and 1. Okay, so here is a superposition. So this is the state 0, this is state 1. Okay, these two states are orthogonal to each other, but the single qubit is expressed as a superposition of these. The coefficients are alpha 0 and alpha 1, and if this qubit is normalized, then the sum of the squares of the coefficients goes to 1. So this is the standard statement of expressing a normalized vector in the Hilbert space. Okay? So this is a single qubit. The coefficients may be complex, and there are two of them, alpha 0 and alpha 1. Okay? So the coefficients belong to the complex space C2. Okay? And this is a vector space of complex numbers with dimensions 2, which means that all in all you need how many real numbers? 4 real numbers. Okay? So you need 4 real numbers, and this system, this quantum state, can be described in terms of quantum mechanics, which means that if you perform a measurement, the system will collapse into an eigenstate. Okay, so what will come out of a result of a measurement is not a superposition. You will get only one or the other. So you will be back to either 0 or 1, not a superposition of the two. And if you measure it again, you will keep getting the same thing. So remind yourself of the sequential Stern-Gerlach experiment. Okay? So if you measure the component of the angular momentum in the direction of the magnetic field in a Stern-Gerlach sequential experiment, in which the magnetic fields are all parallel to each other, no matter how many times you do it, you will always get the same result, because the system has collapsed at the first measurement. But if the second measurement is using a magnetic field which is orthogonal to the previous one, then it will put it into a state of superposition. Okay? And the probability with which it will collapse into an eigenstate, either 0 or 1, will be given by the modulus squared of the complex amplitude. So alpha I is the complex amplitude, and its modulus square will give you the probability that it will collapse into the state I, whether it is 0 or 1, but it is going to be either one or the other. Okay? So, this is a qubit, it is a superposition of two states, superposition of dead and alive cat. A photon is in that state because it can be polarized along the x axis or along the y axis, and you can represent a photon state as a superposition of the horizontally polarized component and the vertically polarized component. Okay, both of these are orthogonal to the direction in which it propagates, right? And if you use a polarized sheet which will transmit only the x component and not the y, then it will transmit the x component with a certain probability, and that probability is given by the modulus square of that coefficient. And this analysis is at the foundation of what we now call as quantum information science. So, this is the qubit. You have two complex numbers. Each complex number consists of two real numbers. Okay? This is the probability that we get. It is normalized so that if you sum the square of the modulus, you get unity. And if you use a basis set to span this Hilbert space, then the basis set consists of these two vectors 0 and 1. These are the eigenbasis vectors, and this is called as the standard basis, or in computational literature it is called as the computational basis. Okay. So, this is the standard basis, this is the terminology which is used, or else the computational basis. So, whenever in literature you see that they are talking about a computational basis, they are just talking about 0 and 1 as the basis set. It can be any linear superposition of the same, because they are all equivalent. But if the basis is actually 0 and 1, then it is a computational basis, as it is called. All right. So, now I have written the complex numbers using polar coordinates. Okay. So, the first is rho 0 e to the I phi 0, the second is rho 1 e to the I phi 1, right. And this is normalized, so you can always write it as you can write the coefficients in terms of cosine and sine functions, because for normalized states the sum of the squares of the modulus square of the complex amplitudes will go to unity, and that is a nice property that the cosine and the sine functions have, that when you take their squares and add them up, the cos square theta plus sine square theta always goes to unity, and you can absorb the phase factor in this e to the I phi. But using half angles is something that you will find to be of great advantage now, and this is for a reason of representing the qubit on what is called as a block sphere, which I am about to describe. Okay. So, in order to take advantage of how we will represent a qubit and how we will compose logic gates on the qubits to develop quantum computers and quantum circuits, okay, we will do so by representing a qubit on what is called as a block sphere, and when we do that, the advantage of using this half angle will become very clear. So far as using the coefficient itself is concerned, it could be the cosine and sine of any angle, but we are going to use half angles. So, you can have a photon qubit, you can have an electron spin qubit, which is again a two state system, all right, the spin up and spin down, because the electron is a half integer Fermi particle, right, and therefore, with reference to the axis of quantization, it can be either up or down, and you can use it as a qubit. You can use any quantum system which is in half integer angular momentum as a qubit. It can be an atom, all right. It could be a defect in a solid. If it happens to have an angular momentum of half, then you can use it as a qubit. And technology indeed uses many different kinds of variants of this. And a two-state system you can represent using these coefficients alpha 0, alpha 1. You represent the unit, the computational basis as 1, 0 and 0, 1. So, 1, 0 is the state 0 and the 0, 1 is the state 1. Okay. So, that is the terminology. All right. So, the ket 0 is the matrix 1, 0 and the ket 1 is the matrix 0, 1. So, this is the qubit. Okay. You have 4 real numbers, but you actually need only 2 real numbers. The reason is there is an overall phase which is arbitrary. An overall phase angle is arbitrary because the angle is measured with respect to some reference. Like in a plane, you measure it with respect to the x axis and say that, okay, if a point on the plane is somewhere, then you draw a line to the origin and ask what is the angle it makes with the x axis, right. But where you are going to place the x axis is arbitrary on the plane. Okay, you can draw the x axis over here or here or here, any which way. So, the angle becomes arbitrary. So, there is an overall angle which is a real number, which is arbitrary and you can dispense with it. And then you have the fact that the sum of the coefficients, the sum of the squares of the modulus of the coefficients is always unity. So, that reduces, that puts one constraint, which reduces the number of real numbers that you really need from 4 minus 1 to 3, and then again you need 1 less. So, you need only 2 real numbers to specify the state of the qubit, okay, because of this normalization condition. And if you need only 2, the best way to do it is to use the polar angles theta and phi. Okay. So, you are going to use the 2 polar angles, and this is something that we are very familiar with in, we use the spherical polar coordinate system in which a point in a 3-dimensional space is represented by r, theta and phi. Now, we are not worried about r because the overall normalization takes care of the absolute magnitude of the radius of the sphere, which is can be set to unity, right. So, that the sum of the squares modulus squares goes to 1, and then any position of a point you can represent a qubit by a point on the surface of the sphere, because you need only 2 real numbers, and these numbers can be the theta and phi, and you remember how these numbers are defined in spherical polar coordinate system. So, you define the spherical polar coordinate system as r theta phi with reference to a Cartesian system x, y, z. So, theta is the polar angle with reference to the z axis, and phi is the azimuthal angle with reference to the zx plane, right. So, these are the 2 angles theta and phi. So, you can write this qubit by extracting this redundant phase, the phase e to the I phi 0 you can dispense with as irrelevant. Okay. You can set that phase equal to 0, and now you have these coefficients such that theta would go from 0 to pi in spherical polar coordinates and phi would go from 0 to 2 pi, the azimuthal angle, and now you can write the qubit as cosine of theta by 2 times 0 state plus e to the I phi sine theta by 2. So, this becomes a general expression of the qubit. You have taken advantage of the fact that there is an overall phase phi 0 which does not matter, and you have also taken advantage of the fact that the sum of the modulus square of the coefficients goes to 1. So, you can represent a qubit by this, and I have used half angles for reasons which will become very clear now, and you will see the advantage. So, this is the general expression of a qubit, and if you take a point, let us say at the pole. So, this is the north pole of this sphere, if you like. Okay? There is no north star, it does not matter, there is a north pole. All right. This is just for the sake of our discussion. So, look at this point, ask yourself what is its polar angle theta, what is its azimuthal angle phi, okay, and what qubit state does it represent. So, theta is 0, phi is also 0, so theta by 2 is also 0. So, cosine of theta by 2 is 1, sine of theta by 2 is 0, and this is the qubit 0. Okay. What about the south pole? Now, theta is equal to pi, but theta we are using not theta, but we are using theta by 2. Okay. So, it is pi by 2. Okay. And then we are going to use the cosine and the sine of these. So, what is this state? 1. Okay. Now, mind you, 0 and 1 in the Hilbert space are orthogonal to each other. Okay. On this sphere, they are collinear, but this is not a description of the Hilbert space. This is a representation of the qubit using this sphere, and therefore, the angles between them are not going to be the same as what you expect of orthogonality in the Hilbert space. So, sometimes people think that this is a little bit confusing, that why are you representing orthogonal states as collinear. So, there is nothing wrong about it, because you are not even using the same space. This is a different mathematical space, right. This is the space of what is called as the Bloch sphere, and this is named after Felix Bloch, who solid state physicists are very familiar with. So, on the Bloch sphere, these orthogonal states are antipodal, it is coming, one is at the north pole, the other is at the south pole. Okay. So, consider this point on the x axis. What is the theta angle now? Pi by 2, and what is theta by 2? Pi by 4. So, put cosine theta by 2, sine theta by 2, which is now pi by 4, and find out what this. So, this will be 1 over root 2, right. So, this will be a superposition of 0 and 1. Okay. So, this is going to be a quantum superposition of 0 and 1. There is no analog for this in classical digital electronics. Okay. It is a superposition of a switch being on and off. Okay. Even Uday will not be able to construct this, but you will if you use quantum devices. Okay. So, this Bloch sphere is something that we are going to use extensively, and it is very simple, but it is important to do it very carefully. So, let us take the other important points over here on the Bloch sphere. So, take this point on the positive y axis, put the value of theta, put the value of phi, get half of theta. Phi is now 90 degrees, right. So, you have to put those values, and then you get e to the I phi, and then you get I from that, the square root of minus 1. Okay. So, this is the one qubit quantum state whose superposition of 0 and 1, the coefficients involve an imaginary number, square root of minus 1, but that is not a problem, because we are working in a Hilbert space which has complex coefficients, okay, the C2. So, what about this point which is on the negative axis where it intersects the sphere? Here again theta will be pi by 2 and phi would have gone from x to y to minus x, so it would have moved through pi, right. So, phi would be pi in this case. So, it is e to the I phi which is cosine of pi. So, you will get minus 1. Okay. So, this is again a superposition, but a different superposition. And then you have this point on the minus y axis. So, this you can get the same way by putting the values of theta and pi. Theta is pi by 2 as in the previous cases, they are all in the xy plane. So, theta is pi by 2 in every case, theta by 2 is pi by 4 in every case. But now the phi angle would have picked another pi by 2. So, now you will have a minus I over root 2. Okay. So, this is called as Bloch sphere, sometimes it is also called as a Poincare sphere, and this is the sphere on which qubits are represented. So, every point on the surface of a qubit, it does not have to be these 6 major points that we talked about. These are the 6 major points only because we have these Cartesian, the intercepts of the Cartesian axis with the sphere. But there are all kinds of orientations, different axes, and there are infinite points on both the hemispheres. Okay. And there are infinite ways of writing these qubits. And what a quantum gate will do is to pick an initial state of the qubit and move it to a different state of the qubit. Okay. So, this is what your transistors were doing in digital electronics, okay, which is what we talked about in the previous class. So, these are how the gates are built, that using the Boolean algebra you manipulate the zeros and ones so that you can get a desired effect. And now you need to manipulate these qubits. And what is the meaning of manipulation? You need to move them around on the surface of the Bloch sphere. How would you move them around? Just think of a sphere in 3-dimensional space and you want to go from one point to another on the surface. You need to rotate it about some axis through an appropriate angle. So, an appropriate axis and an appropriate angle is what you are looking for. And a quantum gate can be devised. When you are going to do quantum computing, you have to devise a quantum gate that is going to be driven by this consideration, that okay, this is what I am starting with, this is where I want to get. So, this is the kind of rotation I want to bring about, and what kind of physical process can I carry out on the quantum system which will move it from the initial state to the final state, whichever is the desired state. Okay. So, these are our qubits, the pure qubits, right, 0 and 1, and then these are the superpositions. And notice that collinear points which are antipodal, okay, they are orthogonal to each other, remember that, and manipulation of a qubit involves rotation of the Bloch sphere about some axis. Okay. So, quantum gates and quantum computation essentially boils down to manipulating the rotations about some axis of the Bloch sphere. Now, when you get to multi-qubit systems, 2 qubits, 3 qubits and so on, then you have to think of the Bloch sphere in a multi-dimensional space. So, it becomes a little more complicated to visualize, but with a single qubit it is really very revealing and it is a great idea. So I don't think we need to worry about how we are going to visualize these rotations on a multi-dimensional block sphere. So don't worry about it at this point. Just concentrate on the single qubit systems. Okay? So now we have this block sphere. The thing to remember is that you have these orthogonal vectors 1 and 0 in the Hilbert space, which are represented by antipodal points, the north pole and the south pole of the block sphere, right? And an arbitrary qubit is represented as a linear superposition of the dead cat and the live cat, the 0 and the 1, okay, with coefficients for which you need two complex numbers, but you have eliminated one because there is an arbitrary phase, and you have eliminated one more because it is normalized. So you have only two real numbers, theta and phi, and this is your representation of an arbitrary qubit. Okay? Thank you. I will take some questions and we will proceed from here in the next class.
That sphere, block sphere.
You are going to have to do this experiment. What is a qubit? A qubit, at some point, it has to be a physical device, like a bit. In classical computation, has to be a switch. It is either on or off, right? That is what is going to represent 1 or 0. And a qubit is a physical device. It can be a photon, for example. It can be an electron spin. And then you are dealing with a system having half integer spin, and if you want to flip it, then you have to apply a magnetic field, right, so that you can flip it. I am going to discuss that in one of the later classes. Okay? So that is what manipulation of qubits means, and that is the reason it is so hard to build a quantum computer, because you need to control these things at a quantum level. So it's not easy to build a quantum computer. But to be able to build it, you need to understand quantum gates. And what we are going to discuss here is to get some familiarity with the quantum gates, so that we know what a quantum computer will have to achieve. How are you going to manipulate single electron spins? Then you need ultra cold temperatures, all right. You have to go to liquid helium temperatures or micro Kelvin temperatures, and then develop control on these at that level. So it's very hard to build a quantum computer, which is why it is built to a certain extent, but not quite built to a large extent. But it's coming. It's coming.
So we are using transistors for to build this.
You're using much more than transistors. Yeah, with transistors you can build classical computers, and you certainly need transistors for various things. So it doesn't mean that you're going to dispense with transistors, nor are you going to dispense with classical computers. Okay? But they are not going to be enough. You need a quantum bit which you can actually manipulate, and that will give you only a single qubit machine which has limited power. But you need a multi-qubit quantum machine which has enormous power. So you need not only a quantum bit, but you have to entangle 2 quantum bits or 3 quantum bits, and so on. So, but progress is taking place at an amazing speed. So you're going to have to use these machines. Thank you.